Okay, so let me go back on speaker view, and now I will, okay. Okay, so Michael, I'll ask you to unmute, and I will, let's go to questions.
Yes, I have some questions about these things, these bubbles, for example. I would assume if they had some propulsion capability, the bubbles would stay, close to the UAP. They don't move. Now, the question I have is, you show some bubbles there and bubbles that aren't there. I'm curious if the direction of the aircraft is in the same direction or if it went to 90 degrees. And my viewpoints are
90
that—
degrees, 90 degrees. The balloon above the UAP is to counteract the force of gravity pulling the UAP down. It's literally like a balloon. You know, it's a buoyancy that's keeping the thing aloft.
Yeah, but what I would assume is that if there's a bubble involved, it would stay with the UAP and not in a location out there. So what I'm suggesting here is that this might be an artifact.
It did stay with the UAP, except when it actually moved at a certain velocity to the left. At that point, it disappeared. And the other complicating factor for me, just so you know, was they would switch back and forth between 1 and 2 mag, and you wouldn't see these effects in the double mag because the field of view of the detector is now 1/4 of what it was before.
Okay. I guess the one question I have is, in terms of these bubbles, is there any idea how to figure out what the electrical field is or the magnetic field?
Well, we know it's a positive magnetic field.
Why?
Well, because the Earth is considered a negative magnetic field relative to it.
Well, the Earth is a dipole.
Well, not when you're sitting out there in the air. It's like the Earth it's not electromagnetism. You can't really consider it electromagnetism. It's not like
Wait a minute.
Negative charge.
Can you say that? Because, first you're talking about gravity magnetism, and then now we're talking about the effects of it. And then how could you say that it's not electromagnetic?
Because I could, I would suggest you look at my patents, and I have all the figures there that show it. But basically what I could do is I could take and vary the magnetic field direction, because see, it's a magnetic recording disc. And so if I wrote with a positive magnetic field on the surface, it would make a positive field direction on the surface of the disc. I could also—
So then you got to say that the gravitation is affected by magnetism, right?
Well, not directly,
come on.
Indirectly.
Oh,
it's a byproduct of magnetic. The gravitomagnetic induction has electromagnetic effects at the edges, is what I would say. But it's not the same thing. I can change the direction of the electromagnetic field without affecting the direction of the gravitomagnetic field, is the simple answer. And the other reason I know is because a piece of glass will produce the gravitomagnetic field, but no electromagnetic field. There's no little pulses with a piece of glass. Follow? It's not, there's no edge.
No, I don't follow that.
I guess I could show, if I could show them.
Actually, let me, if it's okay, let me move along. Because we're yeah, and I'm sorry about that. Actually, I had a quick one too, if I could ask you to elaborate. Someone had mentioned, and it may have been in APEC, it may have been in another conference. They had said, in their view, there was no such thing as anti-gravity. There was only positive gravity, and that a tic-tac would create lift by creating positive gravity above it. It sounds like when you describe this bubble, it sounds like that might be what's happening. Is that what you're...
Yeah, positive gravity. Gravity to be anti-gravity is positive. Gravity is negative. It's a negative direction, field direction, and one is a positive repulsive field. So yeah, he's right. But what Hal's addition, Hal put us adding to it, is that the positive gravity is a different kind of space-time. It's expanded space-time. The negative gravity, when you're in a stronger gravitational field like a star, that's negative gravity, not positive. It's stronger negative gravity, and that's why you see GR effects like time slows down on the planet Earth compared to outer space.
So it's possible then that and again, I'm not using a good thought example, but it's possible that the UAP is, instead of pushing against the Earth to stay aloft, it might actually be pulling itself up.
Exactly.
Okay.
It's pulling itself up. And so essentially when it's creating a warp drive, that's what it's doing. On the left side, that dark region, it's creating that pull field. It's creating that expanded field. And then on the right, where you see the lighter, the brighter regions, that's where the gravitational field is getting stronger. So one side it's weaker and one side it's stronger, and it creates the mystery in my mind is the bow. How does it pull the bow? How does it create this buoying force? And I kind of thought about it. It's kind of like if you're, remember when you were a kid, you'd go on the whirly go round in the park, and you'd go run around the edge, and then you'd get on it and it'd spin around, and then if you got off, you'd be all dizzy. Do you remember that? Well, think of that. Some of them, they have like a bar that goes to the center, and if you got that thing spinning around really fast, and you're at the edge, and then there's 4 of you, and you all pull yourself to the center, what happens? The thing goes faster. Okay, that's how it's using torque basically to make the thing spin up. Well, I think that's what's going on with the UAP. It's doing that to create this acceleration that it needs.
Okay.
Kind of like in the video. Remember the movie Back to the Future, when they got in the DeLorean, and then they get it accelerating. They get it up to a velocity, I think it was 88 miles an hour or something like that, and then they like boom, then it disappear. Well, it's back to the barrier problem in the tunnel dial, except that instead of tunneling in, we're tunneling out. You can tunnel both ways.
Okay. And I just had a note from Todd Desiato, but let me go to other questions. Does anybody want to raise their hands in chat? I have a lot of comments that I'm sorting through for questions. That's why I'm struggling a little bit here. So here's one from HT Alvarez who'd asked, and sir, do you want to ask that directly? HT. Here, let me ask to unmute. Okay, it looks maybe his connection is bad. He was asking, does writing or reading a cavity on a bump, or reading cavity or a bump on the disk, cause a nanopropulsion force on the magnetic particle on the disk?
Okay, say it again.
Oh, sorry. So he was asking, I think he was asking, when you're writing or reading a bump on the disk, does it create a nanopropulsion force on the particle?
Writing or reading. Well, write and read goes, in my mind, when I think of read and write, that's what the head has, a little magnetic coil called a transducer that you put an AC signal into it, and it writes, and it makes a little magnetic domain on the surface of the disk that matches that. And then what I'm using is the read sensor, which is a special magnetoresistor, it's called, and it reads back the data as a positive or a negative direction, polarity, magnetic bit, it's called. But the bump I didn't make with the head right transducer. I made it with a focused ion beam. It's an actual physical feature on the surface of the disk. So I can't erase it. But the other thing that's kind of interesting that he raises is, in order for me to do this, I had to erase the disk. I couldn't do this if I had all this data written on it, because all I'd see, it'd be swamped out by all that data. So what I did is I actually erased the surface of the disk, which erasing is basically making it so all the little magnetics point different directions, so that there's no magnetism on it. So in any case, I don't know if that answered his question or not, but that's the best I think I can do.
Yeah, absolutely. You know what? Let me go to Gravity Alchemist, and I think that's Bill, I believe. Sir?
Unmute. Hi, do you hear me?
Yeah.
Okay, great. Hey, that was a great presentation, man.
Thank you.
Way over my head. Like I said, I'm not a trained scientist, but I do have an aptitude for science. But so I look at a lot of stuff on the internet, and this one fellow's always talking about pressure mediation. So to me, it seems like it's like a pressure mediation of gravity. In other words, your gravitomagnetism is in Einstein's idea that when I read about his theories about acceleration, is basically no different from gravity. And I always think that those are pseudo forces, but they're real. You feel them depending on which frame of reference you're in. If you're in an inertial frame of reference or not inertial frame of reference, these kinds of things. So this gravity, magnetogravity, and acceleration, do you see those all as the same thing? Is in other words, I'm trying to get my head around this. Is magnetism some type of accelerative force that's pressure mediated in your construct of that balloon above the TikTok? Or am I making any sense?
Yeah, no, that's a good. I think that's a fair way to conceptualize it. It's kind of like I said, it's kind of like a balloon, like a physical balloon. You go on a balloon ride. That's the first anti-gravity craft we developed. Right?
Yeah, I think it's really basic terms. Like I can understand your merry-go-round analysis. I love merry-go-rounds, and the whole idea of what are like Newton's spinning bucket. Really, what are those? What is really happening?
You could look at. So let's talk about the spinning bucket. Okay, you could imagine that. Okay, this let's go back to the whirly-go-round. Okay, you're sitting on the edge of this thing, and it's spinning, and you're holding on the bar there. Okay, what happens if you let go?
You fly off perpendicular to the axis of rotation.
It literally pushes you off, right?
Yeah, at a 90 degree, you fly 90 degrees.
And follow that up with what's at the center of gravity of the spinning disk you were on? Nothing. It's empty.
Correct.
There's nothing there. So how does nothing push you off that spinning disk?
Exactly.
Okay? Well, think about it. Okay. And
yes,
then
sir.
Think about how long did it push you off? Well, only for a few millimeters, if that much, even a millimeter, that's where it was pushy. Once you're let go, you fall on the ground. Gravity takes over and you fall on the ground. Okay.
So I see that as a steady. You go back to
empty space is pushy.
I see you go into a steady state. You don't feel any forces. When you let go, and all of a sudden that force isn't on you anymore, you're in a steady state. And
okay,
then
let's do the bucket problem now. Do the bucket problem. So you have these amusement park things where you get inside this big giant tin can, okay, and you strap yourself up against the wall, and the thing starts spinning around, and then the floor drops. Okay. Well, something's pushing you up against the wall. Well, again, what's at the center of gravity of that spinning can? Nothing. Nothing's at the center of gravity, and it's pushing you up against the wall. Now, what happens if you push yourself? Say you had a spring on your back, and you could just like push this little button, and it would push out a little bit. What would happen? Same thing. You'd go boing, 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 hit the ground. Okay. It's only strong at the membrane. It's only strong for a very small distance. Okay. And it's associated with the absence of matter. So there you go, all around you.
Awesome. Okay, so I should apologize. I'm trying to get through these. Jacob Helvey had asked, Jacob, do you want to go? Yeah, there we go.
Let's see here. Oh, yeah, it's just really just a quick comment.
I like your background, Jacob.
Thanks. No, it was really, I thought that video, the background, not mine, but from the video is of the ocean. Am I incorrect on that?
The background of
I thought the perspective, yeah, the Tic Tac video.
Well, I believe it was at like 20,000 feet. So I don't really think that would be an issue. And in fact, there were 2 other videos that they had, the Navy released, that were more.
Might have been the other one, because
and those other ones were right close to the water. And I couldn't see, I don't even know if those are real, to be honest with you, because those don't show any of those same effects that I thought in the 2004 Tic Tac video.
I was just thinking, it's just a comment, if that was the case, that it could have been some sort of surface reflection from the ocean, if that was the...
yeah, but not at 20,000 feet, I would.
Right, so this could be a different video.
Yeah.
That's all.
No problem. I appreciate your question.
Awesome. Oh, let me go to Wayne next. Wayne, go for it, sir.
Hi, I apologize. I wasn't able to hear most of the presentation. One thing I've been wondering is how would you recommend measuring gravitomagnetism in an experiment? Because I'm going to be looking for those kinds of effects very soon. I'm going to be working with some superconductors.
Sure.
Just wondering how you recommend setting up instrumentation to detect.
My recommendation is this: you go and you find some old hard drives, okay, and you take the lid off the hard drive, set it up in your computer like you're going to use it, right? You know, you can buy these adapters that let you plug it in external to it using a USB connector. Take the lid off. Learn the electronics, fit where the head is, where the read write. There's wires on there, and there's like certain wires that go to the read head. It's a little resistor, microscopic resistor, and then it goes to what's called a post amplifier. So you want to find these electronic components. The first way to start though is find your data channel. You know, just take it and hook it in, find out there's like a data channel. It's like 2 wires on the output. And you should be able to hook that up to your oscilloscope and look at the data as it's coming. It'll look like little square waves. Then you trace it back to where this wire is that's coming from the read write head. And now when it's sitting in the middle of this thing, it's parked over this region where these nanobumps are. Every hard drive on the planet has my invention in it. Okay. We just don't know what's there. Okay. I found it in '98. So I didn't even know what I found. So, but in any case, if you can get to look at the data channel and then read it and go back to those 2 wires that are in the read head, then you're in a position to see if you can see the nanobumps in the texture zone. Now, what I had to do to make it work, the only secret sauce was there's a bias current on the read head that I had to adjust a little. I had to increase the bias current a little bit for those nanobumps to show up. But basically, that's how you do it. You could do it just basically using existing stuff.
Huh. So it just picks up little spikes or whatever on an oscilloscope.
Well, first what you do is you'll see like what data looks like. It just looks like a bunch of little square waves. It's a 0, 1, 0, 1, 0, 1. It's not going to be like perfectly square. But you want to trace it back to, so that's a digital output. So basically, this analog signal from the read head goes into a thing called an analog to digital converter. Okay.
Yeah.
So that's why you can't use that part, but you can trace it back to that A to D converter, and then there's an analog signal coming out from that post amp to the A to D converter. That's where you want your connection. Okay. But then you're also going to need to figure out where the two wires are, because you may need to add a little bias current to get it to see the gravitomagnetism. That's basically the simplest way, simplest experiment I could describe it.
Okay. Okay, thanks very much.
Sure, you're welcome. Good question.
Appreciate it.
Thanks, Wayne. So before I go back to Gravity Alchemist, actually, I had a quick question about, so Michael, you'd said that you thought that the UAP was trying to overwhelm the sensor to try and disappear or use some kind of a stealth.
Yeah.
I mean, I guess what's your take on that? That's not necessarily a technical question. I guess that goes more towards intent, but.
Well, it is kind of a technical question, because I think that, I can't remember, you know, Jack Sarfati?
Yeah.
He's got, he's one of my heroes. I really respect that guy a lot. I think that's what he's talking about a lot of times when he's talking about different refractive indexes and negative refractive indexes and stuff. That's what I think's going on there. I think it's changing it's optically changing the way you're viewing it, and it's not doing it by, it almost looks like it's changing its surrounding somehow, so that it looks, that's why I said it was kind of like stealth. But the thing about infrared is it sees heat, and so that's why I don't think it worked. And I think that whoever controlled the UAP wasn't happy about that. It almost seems like we weren't communicating with them in a non-violent manner, and that makes me feel concerned for our well-being as well as theirs.
I see what you're saying. I see what you're saying. So let me go back to Gravity Alchemist then, and thank you.
Sure.
Okay. You had a slide on that had an expanded space-time showed an indention. And then your dense space-time showed a little bump.
Right.
So your space-time definition with those two slides, could you tell me a little more about that? Why was the dense space-time had a bump and the expanded space-time had an indention? What looked like they sort of fit together.
Okay, so, well, they would fit together, and that's why I picked those dimensions, is because what I found is it's really more area dependent than it is depth dependent. So that's why I wanted to show two of the same area, so that you could see that the time dimension was the same. I could see the same prop delay between the electromagnetic signal and the gravitomagnetic signal, 1 microsecond for that area. So that was what that meant is, if the time was constant, then something else had to change. And what changed is you had more space when you had a pit than you had when you had a bug. And that space was between the sensor and the feature, as I call it, the pit or the bug.
So you're saying, so then in a sense that, well, I've seen videos too. I watch a lot of videos The space between all these whatever the liquid superfluid or whatever space-time is, the spaces get smaller between I can't really determine what I'm talking about as far as space-time goes. Is it
seems, think of it like this. You can have water and you can have mercury. Okay. Mercury is liquid too. The space-time in the mercury is denser than the space-time in the water. Okay, I can boil the water and it'll turn into vapor. That space-time is even less dense than the liquid water, and so it's a medium. Okay. We're talking about the medium changes. So when I think of empty space, like out in outer space, I don't think of it as empty anymore. I think of it as having an intrinsic proton flux. Just like in a semiconductor, there's what are called extrinsic and intrinsic semiconductors. Well, I think space-time is like that. There's a certain density of protons flux in outer space, and it's different than from Earth because what's missing is electrons. Okay, so you have, and that's why when I show the universe, I show the futures where it's all empty space, because that's what happens. And that's because of if you think about the proton flux affects radioactivity. Well, if you think of the past, when we were close to the black hole's event horizon, all matter was stable. Even uranium and plutonium, all that stuff was stable matter over there. But as you get over to the left, to the right, where the emptiness is, all matter becomes unstable, and all you got left is a bunch of protons.
Well, Michael, thank you, sir, very, very much. Let me lower Eric's hand here. Eric, I owe you an apology, and Gravity Alchemist, I owe you an apology for muting you out. We're at 2:01, so we're a little bit over our time. But again, let me put it back on gallery view. Everyone, a giant hand for Michael Boyd. Thank you, sir. That was a big presentation. Thank you for sharing that whole thing with us.
Sure. Sorry for all my technical glitches.
Oh, no worries at all. No worries at all. Thank you again.